get started. We talked about Laplace transform last time. You can think of it as a generalized Fourier transform. Generalized Fourier transform. And we also talk about regions of convergence, ROC. Okay, and then Bible. Stability. So let me please you again that if I have the complex plane, sigma j omega over here, and then S is to the sigma plus j omega. Okay. So if I have a system whose Laplace transform, okay, whose Laplace transform have poles like this. Where is the region of convergence of this Laplace transform? To the right of the poles. Okay. Even if I have some of those poles aligned like this, I pick the rightmost pole, and then the ROC is over here. Okay. And then the next question I have for you to see if you actually pay attention in the last lecture is this system is Bible stable? No. Okay, this is not Bible stable. In order for a system to be Bible stable, all the poles have to be to the left of the imaginary axis, or on the left half plane. This is called the left half plane. This is usually called the right half plane. And then the region of convergence will be such, and it contains the imaginary j omega axis. And if that is true, we know this fact that when S is equal to j omega is equal to h of j omega. Okay, this is the Laplace transform of h of t. This is the Fourier transform of h of t. Okay? So the poles have to be on the left half plane in order for a system to be Bible stable. Okay? Yes?
Can you explain again exactly what a pole is?
What a pole is? Okay, a pole is a point where the function, like the Laplace transform, goes to infinity. So S equals to 1 is the pole location. Okay? And if you had a course in complex variables, this is a simple pole. You can have other kinds of poles. This is a higher order pole. This is also a pole, but it goes to infinity a lot more rapidly compared to a simple pole. And you can have a system where you might have something like this, plus b over s minus a squared plus c over s minus d squared. Then this system has three pole locations. One is that s is equal to 1, the other one is s is equal to a, and the other one is s is equal to b. Okay, that's a very good question as to what a pole is. So a pole is the point on the complex plane where the Laplace transform goes to infinity. Okay, it goes to infinity. And it's called a singularity in complex variable theory. So are there any questions regarding what a pole is? Okay, so a pole is the point on the complex plane where a function goes to infinity. Okay. And there's a joke about poles. You want to hear that?
It's already funny.
Okay, if it's funny. Okay, there was an airplane carrying a group of Polish immigrants to America, and they flew into New York City. And then as it flew to New York City, the plane flew past the Statue of Liberty. And then the pilot said, well, look to your right. You see the Statue of Liberty. This is the land of opportunity. You know, you're coming to this great land. So all the poles moved to the right half plane. And what happened to the plane? It became unstable. And it crashed. Okay? So you remember?
Wow.
So you remember this video? You remember that sports have You're taking a memory, right? Okay, let's talk about properties of Laplace transforms. So Laplace transforms are defined for causal functions. Okay. So if I have two functions that look quite different and one being not causal, okay, f1 of t being looking like this, okay, and then f2 of t being looking almost exactly like that, but being causal. That means for t less than 0, it is 0. Okay. It turns out that the Laplace transforms of these two functions are the same as each other if f1t equals f2t for t larger than 0. Because Laplace transform is always defined to be like f1 of omega, f1 hat of s is equal to 0 minus here is very important, f1 of t e to the minus sd dt. Okay? And then f2 hat of s is defined to be 0 minus infinity f2 t e to the minus sd dt. And these two are the same integration, and so they have the same Laplace transform. We go without saying that f1 hat s must be equal to f2 hat s. Is this clear? Okay. Why do we always start from 0 minus? Well, we always start from 0 minus to account for some unusual cases. That if f of t is equal to, say, delta t plus, say, u of t. Okay? Say this is f1 of t, f2 of t is just u of t. And if I apply the Laplace transform rule, I will find that f1 hat of s is equal to 0 minus to infinity delta t plus u of t e to the minus st dt. If the 0 minus had not been defined here, the first integration would have been undefined or ambiguous, okay? Because delta is a delta function that peaks at 0. If I do not define my integration to start from 0 minus, the first integration would have been ambiguous and undefined, okay? So the 0 minus is defined to account for cases like this, whereas it doesn't matter actually. The second function is always looking like this. And then it doesn't matter whether you start with 0 minus or 0, you always pick up the same integration area. Okay, so for functions like this, it doesn't matter. But for functions that has a singularity, it does matter. Okay? So if I look at example 11.8, okay, I am asked to find the Fourier or Laplace transform of this thing over here. Okay, this thing does not have a Fourier transform. because it does not converge. It grows with time. However, you can define a Laplace transform because this thing looks something like this. Okay. And to find the Laplace transform, you would perform the integration. It doesn't matter for this function whether you start from 0 or 0 minus. Okay, t ut e to the minus st dt. Ut is always equal to 1 within this range of integration, except for that very tiny bit at the very beginning. But at the very tiny bit at the very beginning, the area that it contributes to this integral is 0. Mathematician says that the very beginning part contributes to 0 measure, has 0 measure in terms of contributing to the integral. So it doesn't matter whether you start at 0 or 0 minus for this particular integral. And so you can actually replace this integration with that. And we know how to integrate this. There are two ways you can integrate this. Can you mention the two ways that you can integrate this? Integration by parts is one way, and the other way is? Yes? Okay, the other way is to use the derivative rule. Okay, that by noticing that ddt of dds of e to the minus st is equal to t e to the minus st. Right? This is true. So I can replace this integration with minus dds of 0 to infinity e to the minus st dt. Right? Because that derivative of the exponential function gives me the t e to the minus st. And then I can integrate the inner integral, and that gives me e to the minus st minus s 0 to infinity. And assume that I pick s so that the upper limit always vanishes. Okay? So I would have minus dds 1 over s as my result. And then if I differentiate this, I get 1 over s squared. So the Fourier transform of this thing is just 1 over s squared. You can also obtain that using integration by parts. Okay. Okay, so if you were to time delay this, if you define a new ft or pt, this is the time delay version of this one. Okay, I'm sure you know how to do this integration. Okay, just shift it to the right. So I won't go through the detail of this derivation. Okay, but what happens is that if you time delay this thing, you actually have something that looks like this now. P of t. You have something that looks like this, and t is equal to 1, this is t, p of t looks something like that. So you have to perform your integration with a proper delay. Okay? And actually we can do that if you want to. It's not too difficult to do that. So if I were to find p hat of s, it will be equal to 0 to infinity t minus 1 u t minus 1 e to the minus st dt. And this is the same as integrating from 1 to infinity. For I can actually do a change of variable here. Letting t minus 1 is equal to t prime dt is equal to dt prime. Okay? So if I do that, then my integration becomes t prime u of t prime e to the minus t is equal to t prime plus 1 times s over here. Okay, then I have the t prime out here. And then my integration now goes from when t is equal to 0, t prime is equal to minus 1 to infinity. But because of this unit step function, it always makes it back to 0. Okay? So, and if I take out the extra factor, it would be s times 0. This always becomes 0 because of the unit step function, t prime e to the minus t prime s dt prime. So I have the same integral that I have to perform over here. Okay? And it's actually equal to e to the minus s f of s, because this part is exactly the same as this part over here. So this is a time delay property of Laplace transform. If you were to time delay it, you add a phase factor to the Laplace transform, just like what you had done in Fourier transform before. Okay, except that you add this phase factor. Okay, in general, if ft Fourier Laplace transform to f hat f t minus t0 Laplace transform to e to the minus s t0 f hat of s if t0 is larger than 0. Okay, this fact is only true when t0 is larger than 0. Why do you think is the reason? Or what do you think is the reason? Why has t0 be larger than 0? Yes?
Otherwise, it has no effect. It'll get cut out because the integral goes from 0 to infinity.
That's right. So if you have time advanced the function, that was the time delayed version. So had you time advanced it so that you had ut plus 1, t plus 1 instead as the Laplace transform, then the plot of this function will look something like that. But by the definition of Laplace transform, we always integrate from 0 minus. Okay, we always integrate from 0 minus. So we start integrating from this point onward. And I will get a different Laplace transform. And I cannot use the time delay property for this Laplace transform because it looks quite different compared to that function. This function and this function still looks very different. But what I'm actually Laplace transforming is actually a function that looks like that. Okay, and that two functions are quite different. And you cannot use the time delay property for a function such as this, which has been time advanced. Okay, so example 11.9 is one of such example. Okay, in order to find the Laplace transform of this, the textbook went through finding the Laplace transform of this, and when you have this function t plus 1, because of the way we define Laplace transform, we always have to replace this with a unit step function. So this function can be looking like that, and replace with that simplification, then the textbook called this function q of t. And q hat of s will be equal to 0 to t, or 0 to infinity, t plus 1. I will not go through the detail. It will be just that. Okay? It will be just that, and then it doesn't fit into your integration model, but I'm sure that you can break into 2, t equal minus st dt plus 0 to infinity e to the minus st dt. And we know how to do both of those integrals well. You know how to do both of those integration well. And hence you can say that qs is just 1 over s squared. We know how to Laplace transform the first term. We also know how to Laplace transform the second term. Okay. So this is an example where the pole is not a simple pole. It is a higher order pole. In this case, it's called a second order pole. Okay, this is an nth order pole in complex variable theory. And this is a second order pole, this is a simple pole. Okay?
Would you say that it's 0, C2?
What is that?
Would you say that it's, the proper way to say it would be 0 to the C2?
The pole with multiplicity 2, and there are some people say that. This is a pole with multiplicity 2. Okay, an nth order pole. Okay. Why is it called a pole of multiplicity 2? Because it is as if you have two poles. Okay, so if I have a function of s that looks something like this. Then this function has two poles. One at s is equal to 0, and one at s is equal to epsilon. Okay? And as I make epsilon goes to 0, if epsilon goes to 0, then the two poles coalesce. Okay, they coalesce on the complex plane and they become one complex or high order pole. That pole location, okay, when epsilon goes to 0, you get this higher order pole, second order pole, or pole with multiplicity 2. Because it's actually two poles coalescing at that point. Okay? So you can give that name to that pole as well. And then there's another example which is rather complicated, but I wouldn't derive it. But you would know how to do that. Okay, example 11.10. Okay, actually this is example 11.9. Example 11.10 gives you this example of f of t e to the minus alpha t cosine of omega t u of t. Let me see what the textbook call the name omega. Okay, omega d calls it omega d. And how would you find the Laplace transform of such a complicated looking function? What is the first strategy that you should use given such a complex function? Do you do integration by parts, or you do something cleverer than that? You replace the cosine with exponential. Okay, you use the Euler's identity, replace the cosine with exponentials, and then you have sums of exponentials. And exponentials are a lot easier to integrate. You integrate term by term, you get some complicated looking functions, and then you combine them. Okay? So, after doing all the hard work, this is the result. Okay? And if you stare at this result, does it have a pole? And if it does have a pole, where is the pole located? The pole is given by the value of s such that the value of the denominator goes to 0. Okay, so you find the location of the pole by setting this to 0. So you get s plus alpha squared. Okay, you take the square root of this. What do I get when I take the square root of this? Yes? I get plus or minus j omega d. Okay? Plus or minus j omega d. And hence I get s is equal to minus alpha plus or minus j omega d. Okay? So, taking the square root of minus 1 always gives you two possible roots. That is very important. If you don't take care of that properly, you can be misguided. Okay? You can be misguided. Now let me give you a very simple proof. Square root of minus 1 is equal to j. Right? So square root of 1 over minus 1 is also equal to j. So this implies square root of 1 over square root of minus 1 is equal to j. So 1 over j is equal to j. So if I do that, then I get 1 is equal to j squared. And you know that this is wrong, right? J squared is equal to what? Negative 1. So I arrived at that proof, erroneous proof. J squared equals 1. What did I do wrong?
1 over j should be negative. Yeah, negative j.
No, I multiply across. I do a cross multiplication here. I get 1 is equal to j squared. Right? So apparently there's something wrong somewhere in my logic. And I just want you to search where the logic is wrong. Okay, you go home and search for the problem with the logic. Okay, I will tell you where it went wrong. You can ponder about it. You can meditate about it. Tell me where it went wrong. So you have j squared is minus 1. So you have 1 minus j squared is equal to 0. You have j squared is 1. 1 plus 1 equal to 0. So 2 equal to 0. Yes, Alex, what do you think?
So in that that square root, you have 1 over negative 1 is equal to j, but when like you like split it up into like root 1 over root negative 1, shouldn't there be like a root 1 in the numerator above that j over there?
Yes. Root 1, right? Root 1 is 1, isn't it?
Oh, so you still need it in the numerator though then, right?
Yeah, root 1 is 1. Root 1 equals 1. Root of minus 1 is j. Right? So you go home and figure out what went
on the
wrong.
right hand side, you just do j.
Okay.
Yeah, I just need this.
When you take the square root of it, you have to make the negative 1 be at the top. So you can move this.
Yeah, it doesn't matter.
So I just went through the time delay property of Laplace transforms, so I won't go over that again. There are several examples on time delay properties, so you can figure that out. Then what is more interesting is the time derivative property. This is a very interesting property of Laplace transforms. Okay, time derivative property. Okay. And this is actually quite different from that of Fourier transforms. So if we have a Laplace transform, okay, of a function f of t, Laplace transform to f hat of s, what does this Laplace transform? Okay, what does this Laplace transform to if it were to differentiate f prime of t? I mean f of t and get f prime of t. So you can actually go through a simple mechanical process of Laplace transform. Okay, you be very careful with the 0 minus when you apply this formula. Okay. And then you came up with the f prime, and the instant reaction you have is to do integration by parts. Okay, you do integration by part, and then you get f of t e to the minus st. Does anybody need a revision on integration by part formula? I can derive it very quickly if you can't remember what it is. Okay, so what you do is that you identify the one that is an exact integration, integrate the part first, and then evaluate this at 0 minus infinity, and then you put a minus sign there. And then find the thing that you have, put the thing that you have exactly integrated there, and then you differentiate this one. If you differentiate this one with respect to t, you get something like minus s over here. Okay, then you have this integration to do. So this is the integration by parts formula. And then for the first term, okay, when t equals to infinity, if you pick the proper s, you can make the upper limit vanish. Okay, then the first term would only have this left. Will only have that left. Okay, and then the second term gives you plus s, and this is just the Laplace transform f hat of s. Okay, so you have this rather peculiar rule that if ft Laplace transform to f hat of s, f prime of t, which is the derivative of this Laplace transform to s, f hat of s, minus f prime, or f of 0 minus. Okay, you have this rather peculiar looking rule. And what was the rule for Fourier transform that you have remembered? Just j omega times f of omega. Know that peculiar thing hanging at the back there. Why do we have this peculiarity for Laplace transform? Let's try to understand it. So if I have a function f of t that looks like this, e to the minus t, and this function would go through 1, maybe it can be a. Okay, a, it goes through the value of a, and then it grows. Let me assume that it decays exponentially. Okay, in this case, and then it grows exponentially this way. So this function is given to be that. Okay, and then when we take its Laplace transform, we actually only worry about the function over here, and take the first Laplace transform. Okay, but if I were to find its derivative, it would be a e to the minus t. Okay, and then its derivative will look something like this: minus a going to 0 like that, right? So if I were to find the Laplace transform of this derivative, I only worry about this area over here. Okay? However, if my function is causal, these are non-causal signals. Okay, if I have a function that's causal, and it looks something like this, u of t. It will look something like this, and exactly the same as that function, except that it's 0 for t less than 0. Okay, this is my causal function. An exact replica of that, except that is causal. Okay, if I were to differentiate this, what do I get that is different compared to that picture over there? If I were to find the time derivative of this, to the right, I will also have an exact replica of that thing over there. But what do I have to add to this picture to make its derivative correct?
Delta function.
Yes?
Delta function, right?
Yeah, instead of TA answering, what about students answering it? What about Alexander over there? Hamidi, right? Alexander Hamidi.
It would be a delta function.
A delta function. Okay, what amplitude is this delta function?
A.
Yes? amplitude, the magnitude of this delta function is A. Okay. Actually, it starts from here. It has a delta function of magnitude A. Something like this over here. Okay, you have to add that part in. So now if you find the Laplace transform of this and the Laplace transform of this, they are different. This will give you an additional term. Okay? So this A is actually the value of this thing at 0. Okay? At 0 minus or 0. Okay? So the Laplace transform of this is not the same as the Laplace transform of that. So that's why when you take the derivative and find its Laplace transform, this actually is the Laplace transform of the causal function. Okay? And we actually have a non-causal function when we take its derivative. And in order to define that Laplace transform, we have to add this little bit and subtract it out. And that is the delta function that we have to subtract it out. Okay, to get the two to be equal to each other. Is this clear, or you want more detail in the derivation? Okay, that little thing comes about because we are dealing with Laplace transform only exists for causal functions. Okay? Well, maybe we can go through the derivation and show you that that in fact is true. Okay? Say if I were to do the first case over here, then I would have obtained the fact that the Laplace transform of f prime of t, if I were to find its Laplace transform, then I would have just done as a rule